Okay, let's get started. So today we're going to finish off with inverse functions and properties of inverse functions. Then we're going to have a look at piecewise functions. We've done a little bit on piecewise functions before when we looked at the absolute value function. And you would have seen a little bit of piecewise functions also in the last tutorial. Okay, but we'll go through a few more complicated examples. And then that will take us on to limits and continuity, which we will look at next week. Okay, so please prepare yourselves for next week on limits and continuity. It's the next bit of the chapter on functions in the Stewart textbook. Okay, so remember from last time, we were looking at inverse functions. We had some set x. Those that just came in, please get ready so we can start. Okay, please remember when the timetable says lectures start at 1:15, I'll start talking at 1:15. It's not you show up at 1:15. Okay, so recall we had some set x, some set y. We could go from x to y using f. And the whole idea of the inverse function is that we wanted to go backwards. So instead of going from x to y, we want to go from y to x. And we called this f inverse. Okay. So what does this mean? Well, we can start from x, we can go to y, then we get back to x. In other words, f inverse of f of x, this was x. So again, you read it from right to left. So we start at x, we go using f to end up at y, then we use f inverse to go from y back to x. So that was the one equation we came up with on the Thursday. Then we can also go the other way around. So that would be f of f inverse of y is y. So we start at y. Again, read right to left. We start at y. We use f inverse to go to x. And then we use f to go back to y. Okay, we got these two equations on that Thursday. Let's put here and. So for f and f inverse to have the right properties, they need to satisfy these two equations. So both of them must be true for f and f inverse to be inverses of each other. Now, there's another way to check if f has an inverse. So instead of checking these two equations, we can check two properties. If the function f satisfies those two properties, we call it invertible or bijective. In other words, it has an inverse. Okay, so properties for f to have an inverse. We spoke a bit about this last time when we had f going to from x to y, then back to x. We said that middle set, if you remember back from Thursday, it was the target of f. It was also the domain of G. Remember that picture that you drew down? We had x going to y going to z. And then we had the middle y was the target of f, was also the domain of G. And we said that it needs to have certain properties. So we're going to write that down explicitly now. Okay, so the first property is called injective. Okay, it's just the name for the property. You might also see this written as one-to-one. Okay, so what does this mean? It means if we look at the domain and the target, those elements are mapped 1 to 1. So one element in the domain is mapped to one element in the target. So we'll look at an example and a non-example. So let's say we have x and y. So we'll just look at two elements and two elements. There and there. This one is not 1-to-1. We see there are two going to 1. So it's not 1-to-1. This is not injective. On the other hand, if we have something like this, x and y, we got 2 elements for x, 2 elements for y. That one goes there, that one goes there. This is 1 to 1 because we have 1 element from x going to 1 element in y. So again, this first one is a non-example because this is 2 to 1. We want it to be 1 to 1. And then on the right, there's 1 to 1 and 1 to 1. So this is injective. So this first one is not injective, right? Because it's 2 to 1. The second one is injective. This is 1 to 1. Okay, so that's the idea in mind that you want to think of. So 2 inputs going to 1 output, not injective, doesn't work. 1 input to 1 output, that is injective. Okay, let's look at a more function type example. So here we have the function f of x equals x squared. And this is not injective. Why? Because we can pick a point, let's say here and here. So let's say this lies along y equals 1. If we look down at the x-axis, we see we have x equals minus 1 goes to 1, and minus 1, and x equals plus 1 also goes to 1. So 2 x values go to 1 y value, 2 to 1. This is not 1 to 1, so it's not injective. And then on the other hand, let's look at something like this. So f of x equals x cubed. This will be 1 to 1. Pick an x value, you go along the vertical line, it will reach 1 and only 1 y value. For example, 1 will go to 1, minus 1 goes to minus 1. 2 goes to 8, minus 2 goes to minus 8. Okay, it's always 1 to 1, so it's injective. In the first case, it was 2 to 1. That doesn't work. Okay, so those are 2 examples and 2 non-examples for injectivity. So what's the definition? So we have an idea of what it is, but what does it mean in terms of the definition? So definition, a function f is injective or 1 to 1. Okay, it's just 2 words for the same thing. It's 1 to 1. If, and then there's a condition that you can check. If it satisfies the condition, it's injective. If it doesn't satisfy the condition, it is not injective. So if f of a equals f of b, then a equals b. Very, very simple condition. So given a function f, we just need to check this condition. If f of a equals f of b, then a equals b. That's the condition. If it's true, it's injective. If it's not true or false, it is not injective. Okay, one or the other. So let's have a look at an example. So we'll do a non-example and then an example. So let's say f of x equals 2x plus 1. A straight line. Just from the picture, we can tell it's injective. 1 input goes to 1 output. So we expect this to be injective. But let's check. So what do we want to check? We set f of a equals f of b, and we want to check, does a equal b? If it does, it's injective. If it doesn't, not injective. So let's do that. F of a equals f of b. That's our starting point. What do we want to get to? A equals b. If we can get there, it's injective. So on this side, we get 2a plus 1. On the other side, we get 2b plus 1. Okay, we've got plus 1 on both sides. We can cancel that. 2a equals 2b. Easy enough. 2 on both sides. We can cancel that. A equals b. And we're done. It's injective. Okay, so we started with f of a equals f of b. We got a equals b. So it's injective. Okay, so that's the example, and then the non-example. What happens if we have f of x equals x squared? Okay, we already know that this is not injective, but let's go through the steps. So f of a equals f of b. So a squared equals b squared. And now this is where problems start happening. If we have a squared equals b squared, you just take the roots on both sides and you're done. No, you can't do that because you're missing solutions. Whenever you take the root of something squared, you're getting rid of the negative solution because the root only gives you the positive. Like root of 4, that's 2. But minus 2 squared is also 4. You've thrown away that solution. So we don't want to take the root on both sides. Okay, that's going to give you problems. So what we do instead is take the b squared over to the other side. So we get a squared minus b squared is 0. Now this is a difference of two squares, so we can factor this. So this is a plus b, a minus b is equal to 0. Okay, and this gives us two solutions, which is what we wanted. A plus b equals 0. In other words, a equals minus b. We also get a minus b equals 0, so a equals b. The a equals b is fine, okay? But the problem is you can also have a equals minus b. So it's not injective. What we want is the answer to be a equals b and only that. Here we've got a different solution. We've got 2. That's a problem. This is not injective. Right, because we got 2 solutions, we were only looking for 1. Everyone clear on these 2 examples? All clear. Okay, so that's injectivity. Very easy to check. You can draw a little graph to see if it satisfies the test, 1 to 1, or you can use this over here. Okay. Sometimes drawing the graph is very easy. For example, if it's x cubed, just do a little sketch of x cubed, you can see right away. Other functions you might not be able to sketch, but you can do the algebra and you'll get the same answer. Okay. I'll leave that to you. Okay. Any questions on injectivity? All clear on that? Okay. Property number 2 is called surjectivity. So we say a function is surjective. Okay, so a function can be injective. That was property number 1. A function can also be surjective. That's property number 2. It also has an alternate name, onto. Okay, so it can be injective. The other name is 1-to-1. Or it can be surjective. The other name is onto. And we'll see why it's called onto. Okay, but first some examples and non-examples. So let's say we have a function f going from the real numbers to the real numbers, x going to 2x minus 1, something like that. Remember, whenever you're specifying a function, you need to tell me what the domain is, you need to tell me what the target is, and you need to tell me the rule. So here we've got the domain is all of the real numbers. That's fine. It's a straight line. No problems there. I said the target was all of the real numbers. Okay, that's fine. The output is a real number. That's fine. Okay, so let's draw a little sketch of what's going on here. So 2x minus 1, that'll look something like that. Okay, so along the horizontal, we have all of the inputs x. Along the vertical, we have all of the outputs y. So when we're looking at surjectivity, the idea is that the range, the outputs, so the output of the graph, is equal to whatever we set the target to be. Remember, the target we can set to be whatever we want. The range is what we calculate. So here, what is the range? That is all of the outputs. So we see here, it goes down to minus infinity. So this line extends down to minus infinity. It also extends up to plus infinity. So the range for this thing is all of the real numbers. The output is all real numbers. What about the target? The target was all real numbers. So we see in this case, the range is equal to the target. We call it surjective. That's it. So the range is equal to the target. It's surjective. So range equal to target. Okay, again, the range, that's just what you calculate. You've done that in the tutorial. Target, that's what's given to you over there. If they're equal, we call the function surjective. If they're not equal, so if there's stuff missing from the target, then it's not surjective. You're just checking that. Okay, let's have a look at a non-example. So we have f r to r x going to x squared. Yeah. Again, we draw a little picture to see what the outputs are. So we got all the inputs x, all the outputs y. It's going to look like that. Okay, so we got our picture. We can see what the range is. The range is just the outputs. So we see it starts at 0. So over here, the turning point is at 0. And we include everything above. So the range is 0 up to infinity. So from 0 up to infinity, that's the range. What's the target? The target is all real numbers. The range is not equal to the target. It is not surjective. So the range is this. This is not equal to the target. So it is not surjective. Okay. So in this case, it is not surjective. I'm going to change one thing, and it's going to become surjective. So let's look at a new function g. It goes from all real numbers to this new set. So the domain stays the same. The target I'm going to change. I can freely change the target. It's up to me. We're going to go from x to x squared. Okay. The range stays the same. The range is just whatever the outputs are. We just calculate it based on whatever rule is given there. So the range is from 0 to infinity. What's the target now? 0 to infinity. The range is equal to the target, so now it is surjective. Now, do you see how important the definition of the function is? So in the first case, I chose the target to be all real numbers. Me choosing that means it is not surjective. In the second case, the function looks exactly the same. The graph is identical. But in the second case, I chose the target to be 0 to infinity. Now it is surjective. Okay. The graphs are identical. The function rule is identical. I just changed the target, and now it goes from being not surjective to being surjective. Okay. So all of this comes down to what the target is. So if I give you some other target, in this case 0 to infinity, it now changes from being not surjective to being surjective. So please put a big box around the target that we chose for this one, and then underline surjective. And then over here, you put a big box around this target, and this is not surjective. So in both of the examples, everything is identical. The function rule is the same, the domain is the same, the graph is the same, but the targets are different. The targets being different completely changed our answer. Okay, so please make a note of that. So this target, not surjective. If we choose this to be the target, now it is surjective. Okay, please make a note of that. Okay, so that's the idea. Range equals target, then it's surjective. So let's look at the definition. Okay, the definition is a bit wordy, but it's the same thing that we've been talking about. Okay. Range equals target, surjective. Now, the definition just makes it look a bit more complicated, but it's the same idea. Okay, so definition. For all y in the target, there is some x in the domain such that f of x equals y. And we can write this a little bit differently as the range of f. A little bit of notation. We can also write the range of f as f, where we put the domain as the input. Okay, this is just notation. We're not putting the domain into the function or anything like that. We just take it as a symbol like that. It's just notation. Okay, please don't start plugging sets into x squared. Okay, that's not going to work. Okay, it's just notation for the range. And what we want is this to be equal to the target. Yeah. But you can see the similarities. The f of little x equals little y, f of capital X equals capital Y. In the first case, x and y, those are elements of the set. In the second case, capital X, capital Y, those are the sets. But it looks similar to give you the idea. Okay, so again, it's a bit wordy, but let's go through it. So let's say we have a set X. Let's say we have a set Y, some elements in X. I'm not going to number them. Okay, we've passed that. And then Y, something like that. Okay, so let's say we've got this. Yeah. So let's go through all the words there, see what we've got. For all elements y in the target, there is some element x in the domain such that f of x equals f of y. In terms of the picture, f of x equals f of y means that there's a line from x to y because they're being connected. Okay, so what do we have in this picture? The first dot, that's going to some element y. So that element y, that's in the range. We covered this before when we looked at range. Next dot in x, that goes to that element in y, so that's part of the range. The third dot in x, that goes to another element in y. So those two, with the lines going to them, that's in the range. Now let's look at the definition. For all elements in the target. Are we missing anything? It says for all elements in the target. Have we done all the elements in the target? No. The one there, top right, there's nothing connecting it. So this function is not surjective. Okay. Now, if we did something else and we had a little dot there, now we go through the definition again. For all elements in the target, have we used all elements in the target? Yes. So it's surjective. Okay, so that's the idea of this wording. If we use all elements in the target, it's surjective. But that just means the target is the whole range, because the range is what we use. Remember from before? So we use all elements in the target. So the target equals the range. Well, target equals range, it's surjective. If there's anything missing from the target, well, that means it's not in the range. So target is not equal to the range. It is not surjective. Okay. Any questions on surjective? Okay, so please just keep in mind, range equals target, surjective. If the function is 1-to-1, injective. That's all you need to know for those two properties. Okay, property number 3. This is just if the function satisfies property number 1 and property number 2, then we call it bijective. So bijective equals injective plus surjective. So it's a little add-on. So if the function is injective and the function is surjective, then that automatically makes it bijective. Another word for bijective is invertible. In other words, F inverse exists. So if you want to find the inverse, we need to check if it is injective. Then we need to check if it is surjective. If it is both injective and surjective, then it is bijective, and so it has an inverse. Okay, so if we go way back to the beginning here, these two conditions for F and F inverse to be inverses of each other, you can check this again using injective and surjective. Okay, so redraw that picture, X going to Y, going back to X, and then check the two conditions for homework. Okay, so look at the sets X and Y. What does it mean to be injective? So look at the picture and see what happens. What does it mean to be surjective? In that case, you'd have to look at the domain and the range of F and F inverse. Yeah, so that will be for homework. So look at the definition for injective and surjective and try to get back to these conditions here. Okay, so that will be for homework. Any questions on the homework? You're all good with that. Okay. Okay. Finding F inverse. Okay, so to find F inverse, the first thing we need to check is injective and surjective. Let's assume we've done that. We know F is invertible, so now we need to find what it actually is. Okay, we'll start off with a very simple example and then look at something a bit more complicated. So number one, let's write it out fully. So F goes from real numbers to real numbers. X gets mapped to 3x plus 1. Okay, so let's go through it quickly to check if it is injective and surjective. So number one, is it injective? Let's check. What do? F of A equals F of B. We want to show A equals B. So we have F of A equals F of B. So that is 3A plus 1 equals 3B plus 1. We've got 1 on both sides. They can go. So 3A equals 3B. We've got 3 on both sides. They can go. We have A equals B, and we're done. It is injective. Okay, what about surjective? Let's show this quickly. Showing it is surjective is quite easy. So showing it's surjective and finding the inverse, we're going to do that in one step. So we've got here f of x equals 3x plus 1. Okay, we're going to do the two steps in one. Remember the definition for surjective. For every y in the target, there is some x in the domain such that f of x equals y. Okay, so again, for every y in the target, so you give me any y in the target, I need to give you some x that gets to that y. Okay, so again, you give me any y, my job is then to provide you with an x such that f of x equals y. Please make sure you understand that, or else this is going to be very odd to you. Okay, so let's write this as y equals 3x plus 1. Okay, so now we imagine that little thing again. So that y, imagine that's the y you give me. So you give me some y. I need to give you x such that f of x equals y. Again, I'm just repeating what this says. For every y in the target, there is some x such that f of x equals y. Just been repeating that. So again, you've given me this y, I need to give you the x. So, can anyone guess what to do? That y is given, I need to give you x. What do? Sorry? Not substitutes. solve for x. Thank you. That's it. You've given me the y. I want to find x. How do you find x? Well, you solve for x. That's exactly what we do. So y minus 1 equals 3x. X equals 1/3 y minus 1. So the y, that's what you give me. I'll substitute it into here. And my claim is that it gives you x. In this case, it's very easy to see, but let's check. So given any y in the target, this x needs to give y. Again, I've just rewritten the definition. Y from the target, that x needs to give me y. So let's check. What is f of x? So my claim is that this x, that's what does it. So let's write it here. So f of x equals, what do we have? 3x plus 1. Okay. Now you've given me this y. Let's substitute, see what we get. X is going to be 1/3 y minus 1 plus 1. Okay. Let's simplify. So 3 times a third, that cancels. And that gives me y. That's what we wanted to show. Okay, so again, let's go back up here. You give me some y. My claim is that x, if we substitute it back, gives us y. So let's substitute that x, which is what we did over here. And the goal is to get back to y. F of x must be y. So f of x, simplify, gives us y. We're done. Make sense? Okay. And this little step that we did here as a little side working to solve for x, this is the inverse. Okay. Because remember, what was f? F took us from x to y. What does f inverse do? Takes us from y to x. This x equals some function of y. That is, in fact, our inverse. So it's 2 steps in 1. So x was 1/3 y minus 1. This is, in fact, f inverse of y. Yeah. Because remember, what was f inverse of y? Was x. So just a little note here. F inverse of y is x. Because f of x is y. F inverse of y is x. Okay, please make sure you know that. Okay, so we got our inverse. In high school, you wrote the inverse as some function of x. That's wrong. Okay, please don't do that. The function of x is what I give you. F inverse is a function of y. We go back here, right to the top. F, right, normal f, goes from x to y. That's fine. F of x, we all know that. F inverse, look at what it's doing. It's going from y to x. It is a function of y. F inverse is not a function of x. So when we write out our answer, if we go back down here, f inverse of y equals some function of y. We get it from here, from solving for x. Yeah. Okay, please do not give me f inverse of x. That makes no sense. Okay, we all clear on that? Who says no? You said no. I thought it was over there. Yeah? Where did I lose you? Multiplied by 3. This part. The pink one. Oh, that's the red box. So the red box was x. So over here, this x, put that over there. The 3 and the 1. That's let's put some more colors here. The 3 is that 3. The 1, that is the 1. And then the X, I'll put that in pink. Okay. Yeah, it's good to have lots of colors. You can see what goes where. Any other questions? Oh, good. Okay, let's have a look at a more complicated example. Okay, for tests and exams and so on, we won't go anything past some quadratic. Okay, so you can make a note now, quizzes, tests, exams, whatever. It's just going to be quadratics. Okay, solving for the inverse. Later on, we will be looking at inverse trig functions, but we're not going to be solving for them. Okay, we're just going to be looking at some pictures, taking derivatives, and so on. Actually solving for f inverse, it will only be up to a quadratic. Okay, so you can make a note on that. The tutorials may be more complicated. Assessments are only quadratic. Okay, just to keep that in mind. Number 2. Okay, so we've got f. The domain is from 2 to infinity. The target is y. We don't know what that is yet. We're going to figure it out. And the rule is x gets mapped to x squared minus 4x. Okay. So there's 2 parts to this question. Expect the same for your class test coming up. 25th, I think. It was 24th or 25th. Just have a look. You're going to get something like this. Okay. So I've already set your test and June test. So when I say you're going to get something like this, you're going to get something like this. So please make a note. Okay, so 2 parts to this. Determine y such that f is invertible. That's part 1. And then part 2, find f inverse. Okay, so what do we mean by the first part? Determine the set y such that f is invertible. Let's break it up a bit. Y, that is the target. Okay, so make a little note there. Above y, right there, that's the target. Okay, such that f is invertible. What does invertible mean? Make a little note at the top. Injective plus surjective. I don't see a lot of people writing. Everyone, take out your pens. Above invertible, right there, injective plus surjective. Yeah, I don't want to treat you like preschoolers, but if I'm telling you to do something, it's for a very specific reason. Yeah. Okay, so we want to determine y. That's the target. Invertible requires it to be injective and surjective. Which one of those uses the target? Surjective. Okay. So we know that we want to determine the set y such that f is invertible. Invertible, injective plus surjective. Now we know that the target is associated with surjective. So we can read this as determine y such that f is surjective. It must be surjective. And y is the target. For f to be surjective, the target must equal what? The range. Good. So this question we can rewrite as find the range. Everyone clear on that? Okay. So I wrote it like that, but you need to think of what the pieces mean. Y, that's the target. Invertible, injective plus surjective. If we want it to be surjective, the target must equal the range, so we want to find the range. Does everyone see that thought process? Who says no? Where did I lose you? Yeah, so y is the target. Invertible equals injective plus surjective. Okay, what's the definition of surjective? No, check your notes. The surjective, what's the definition? Unless someone wants to help. Yeah, range must equal target. What is y? No, not the range, the target. So y is the target. It must be equal to the range. So we must find the range. Make sense? We want to find y. Y is what we're looking for, right? Y is the target. The target equals the range. So if we're looking for the target, we're looking for the range. Or you can put in brackets, target, same thing. Why? Because they're equal. Range equals target. So if we want to find the set y, we want to find the range. Make sense?
So we want to ignore.
No, we didn't ignore it. What does it mean to be surjective? Range equals target. So there, I'll put there. Right? Oh, we can put here range equals target. Target comes from this, where it is surjective. Surjective means range equals target. We want to find the target. The target is equal to the range, so we want to find the range. Make sense? Okay. So we want to find the range. How do we do that? We got some parabola shape there. How do we find the range? Who said draw? You said draw. Yeah, we draw a picture. Easy. So let's draw a picture. What do we want to draw? F of x equals x squared. Cool. Okay. So what's that going to look like? It's going to be, there's a point there, point there. That's the two x-intercepts. It's going to be something like that. Right? Yeah. Yeah, so that's just the two x-intercepts, 0 and 4. The range is going to be the turning point up to infinity. Right? You just look at the picture. The graph is from the turning point up to infinity. So again, turning points, let's just do that on the side there. Turning points up to infinity. So what's the turning point? -2, yeah. And so that's the x. We don't really want the x, we want the y. So we put -2 and we get sorry? +2, yeah. Yeah. So x is +2. And then the y value is, check on your calculator. -4. -4. That's the one that we're looking for. We're looking for this y value here. Okay, so the turning point is +2 -4. So we're looking at everything from -4 up to infinity. So the range is equal to -4 to infinity. But the range equals the target because it's surjective. So that's y. Okay, so we got y. Okay, so that's part 1. Part 2, find f inverse. Okay, so part 1, we wanted to find y. Well, that's the same as finding the range. So you just draw a little picture. You can see what the range will be. Okay, now the inverse. So we do the same thing as we did before when we were looking at the surjectivity. You give me the y, I solve for x. So we want to solve for x. Okay, so we're going to have f of x is equal to x squared minus 4x. And we have y is equal to x squared minus 4x. Just putting the y there makes it a bit easier because the idea is to solve for some function of y. Okay, little trick. I don't know if you did this in high school or not, but we swap x and y. You know, when finding the inverse, you swap them and then you solve. Same idea. Okay. Or you could just imagine this is x as a function of y, and then you solve it like that. But I think this one you're more comfortable with. So we'll do that. So this is x equals y squared minus 4y. Okay, maybe it's a bit more comfortable like this. Okay, so we have 0 equals y squared minus 4y minus x. Okay, so we get y is equal to quadratic formula, you'll know that, hopefully. So that's going to be 4 plus minus square root 16 minus 4, 1 times x over 2. Or 2 times 1 if you want to put the 2a. Okay, so we end up with this. We can simplify this a bit. So we get y is equal to 2 plus or minus the root of, we can take the 4 out, so it'll be 4 plus x. Okay, we end up with this. Okay, so in high school, you would have done that, you got your answer. Not quite. There's 2 problems here. Problem number 1 is this is 2 plus or minus something. We can't have plus or minus, that's not right. We need to decide, is it plus or is it minus? And we'll see later on what those 2 mean. But if we go back here, over here, we can put in y now, we know what that is. Minus 4 to infinity. Yeah. So now we're looking at f inverse. We're still trying to find that. For f inverse, the minus 4 to infinity, that becomes the domain, because we're going backwards now. So minus 4 to infinity, that's the domain of f inverse. 2 to infinity, that's the range of f inverse, because we're looking the other way now. So that's the range. It is everything bigger than 2. 2 to infinity. Keep that in mind. The range is everything larger than 2. Let's go back here. Now we look at this. 2 plus or minus something. Which one do we pick? The plus or the minus? The plus, because we want it to be larger than 2. So we choose the plus. Since the range of f inverse is 2 to infinity, we want everything larger than 2. Okay, so we take the plus. And then finally, the last step. Remember at the beginning, we swapped x and y. Now we can't just leave them swapped, we swap them back. So we're going to swap them back. We get x is equal to 2 plus root 4 plus y. Okay, you can't just swap them and not swap them back. Okay, swapping them, you're changing stuff. We need to swap them back. But x, that is f inverse of y. And we're done. Okay. Everyone see what we did there? Sorry? Okay, sure. So this bit's okay. Well, why we chose the plus?
Because the range is 2, so that's
Yeah, it must be bigger. Yeah. Good. And then this step here, what we're doing is just
Did you simplify that part in the search in the task?
yeah. So 16 plus 4x, you take the 4 out. Because 16, that's 4 times 4, factor out the 4. Outside the roots will be a 2 that cancels with the 2 at the bottom. Okay, now we've done algebra week 1. I can't do algebra week 3. That's not going to work. Okay. Yeah, please have a look at the algebra notes if you're stuck with your surds and stuff. Okay, so we've got that. In this step, we swapped x and y. And then in the last step, we put it back. So if we swap x and y, then at the end, we need to put them back. Okay, so you can't just leave them swapped. So we swapped x and y, so y becomes x becomes y, and then this will be our f inverse. Okay, now just to show you a picture of what this means, let's see if this works. I did speak to everyone about the Desmos. I think some of you came late for registration issues. Desmos.com, just make a note of that. Very good for plotting your graphs. You will need to be able to plot using Desmos for later on. Okay, very easy to use. Over here, you just put your functions, and then on the right, you see them plotted nicely. And then you can move around. You can look at turning points, intersection points, and so on. Okay, so let's have a look at the function. This was equal to x squared minus 4x. That's what we drew. There's the turning point that we found. But, what? Okay, no questions. Okay, so we've got that. Let's go back up to here. But notice over here, we're only interested from 2 to infinity. So here, let's see if I remember this. X greater than or equal to 2. There we go. Okay. So here, we're only looking at the domain from 2 to infinity. Everything less than 2, the function's not defined. There's no function there, right? Because the domain is from 2 to infinity. That's where the function is. Let's look at the F inverse. I'm going to call it G, right? Because you can't call it something else. So this is going to be 2 plus square root. Okay, ignore the fact that I'm using x. That's wrong, but just go with it. 4 plus x. So end up with, I think that makes it look a bit better. Okay, so the red one, that's what's given. Remember back from high school, the inverse was like the reflection with the y equals x. So look at the red one, and then imagine flipping it over. It's like do it in your head, flip it over, we get the blue one. Everyone see that? Yeah. What happens if we took the other part of the domain? So from 2 to infinity, that's taking the right-hand side. Okay. What happens if we took the other side? So let's say here x is less than or equal to 2. So now we're taking the left-hand side of the parabola. You can't take both. If you take both, it is not surjective. So you have to pick one. I think that's in the tutorial coming up. Okay, so we take the other side. Well, now this plus is going to become a minus. And we see it's flipped over the other side. Does everyone see that? Okay. So if I take the right-hand side of the domain, the inverse gave me that positive 2 plus solution. If I take the left-hand side of the domain, then I choose the minus and I get the other solution. Okay. It always comes in pairs. So choosing the plus and the minus is the same thing as choosing the right-hand side of the domain or the left-hand side of the domain. But that's given to you. That's over here. That's given in the question. Okay. So this part over here, the 2 to infinity, that tells you take the plus or take the minus. Okay, that's always given. You don't pick that for yourself. Okay. Any questions on that? All good. Okay. Then homework on this. Okay, I encourage you to do the homework, right? Remember class test 1. Okay, so we have f of f inverse of y is y, and f inverse of f of x is x. Please check these two. Okay, we all know how to do composition now. You've done the tutorial on that. Look at the first composition, check that you get y. Check the second composition, check that you get x. Okay. Yeah, so please do that for homework. Any questions on the homework? Okay, so everyone knows what to do for that. Okay, so we've got the two functions. You take the composition one way, and then you take the composition the other way. Okay, it's exactly what you've done in the tutorial on the composition with f and g. Right. Any questions on what we've done so far? Okay. Piecewise functions. Okay, so we've done some piecewise functions before when we looked at the absolute value function back in week 1. You would have also seen this in the last tutorial. There was a little section on piecewise functions as well. Okay, but we'll go through it properly. Okay, so the functions that we've seen so far has input goes to output. For example, we can have f going from real numbers to real numbers, x going to x squared. So one rule, you give me x, I give you x squared. Whatever x you give me, I always give you x squared. What happens if we want to have multiple rules? Okay, so maybe for positive x, I want x squared. For negative x, maybe I want 2x plus 1. There's no rules against that. Okay, a function can have more than one rule, depending on what you give. However, we can't write it like this. This way has one rule, x goes in, x squared goes out. There's no way to change that. So instead, if we want more than one rule, we have to split it up into cases. And that's the whole idea for piecewise functions. So we end up with this. So let's say the rule is x squared if x is negative. So if you give me a negative x value, I give you x squared. Then maybe I want it to be x if x lies between 0 and 1. Okay, different part of the domain, different rule. Okay, nothing says we can't do that. And then maybe I want 3 if x is greater than or equal to 0. So what we've done here is taken the domain of all real numbers. You got a question? Okay. So we've taken the domain of all real numbers and we've split it up into 3 cases. We've got case 1, if x is negative. Case 2, if x lies between 0 and 1. And case 3, if x is, sorry, that should be 1. If x is greater than 1. So again, what have we done? We've taken the full domain of real numbers and we chopped it up into 3 parts. So let's say this point here is 0. This point here is 1. Yeah. So look at the first case. If x is less than or equal to 0, that's going to be this part of the domain. If x lies between 0 and 1, that's the middle part of the domain. X is greater than 1, that's that right-hand side of the domain. And we've got a rule for each part. So the first part is x squared. The second part is x. And the third part is 3. So f of x equals x squared for the first part. F of x equals x for the second part. F of x equals 3 for the third part. 3 cases. Okay, so what does this look like altogether? So here we've got x, here we've got y, and we're going to plot this now. And we plot it by cases. Yes? The 3. The 3 is from this. So f of x equals 3. You can write it. That's this pink part. Yeah. I can put more colors. There. Okay. Yes. Yeah, I can put whatever you want, but this is just an example. Yeah. So let's sketch this. So what do we have? If x is less than or equal to 0, it's going to be x squared, but only for x's less than or equal to 0. So we're going to plot it like this. And it's going to stop there. We don't go any further because the function is only defined for x less than or equal to 0. When x is 1, that's something else. We're not interested. So for x less than or equal to 0, we have x squared. Yeah. Everyone okay with that? Next bit. F of x equals x between 0 and 1. So let's say 1 is somewhere here. it will look like that. Notice how I put the open circle there. Remember back from intervals, open circle, not including. Over here we are, not including 1. So it ends with an open circle. And then lastly, it's going to be 3 if x is greater than or equal to 1. So we have a closed circle because this could be equal to 1, so closed circle. And the function just continues as 3. And over here we had f of x equals x. Here you can write f of x equals x squared. Yeah, there's another closed circle here, but you don't really need that. Okay, so again, we took the domain and we chopped it up into 3 parts. Case 1, case 2, case 3. For the first part, we defined it to be x squared. So we draw x squared on the first part. For the second part, we defined it to be x. So we draw x for the second part. For the third part, we defined it to be 3. So we draw 3 for the third part. Notice how there's no overlap between the parts. The first part is the first part, that's it. The second part is the second part, that's it. There's no overlap between the two. And the third part, that's the third part, no overlap there. Okay, did everyone see that? Okay. Just something to point out, at 0, notice how the function changes from x squared to x. It's a changing point. Okay. We'll look at this later when we do limits, but just for now, please keep that in mind. At 0, the function changes from x squared to x. At the point 1, the function changes from x to 3. But it doesn't change very nicely. At 1, you see where the function is? At 3, it jumps up to 3. Okay, so you don't have to worry too much about that. We'll get to that when we do limits. But just notice at these points, the function will change. So when we go from case 1 to case 2, the function changes. Okay, it might be equal at that point, might not be. When we go from case 2 to case 3, the function changes again. Okay, does everyone see that? Yes, okay. Let's look at another example. Example 2. Okay, so I'll put the definition down and then you're going to help me with the sketching. So we have f of x is equal to, and again, we put the curly brace there and we put case 1, case 2, case 3. Or case 4, 5, 6, however many you get. Okay, so this is going to be x if x is less than 0. It's going to be 2 if x is equal to 0. So notice that this function for the second case is defined at only 1 point. Okay? In the first case, it's defined for all negative values. In the second case, it is defined only at one single point. Okay, just keep that in mind. And then it's going to be 1 minus x squared if x is greater than 0. Okay, so we got case 1, case 2, case 3. We're going to draw the domain. We're going to cut it up into the 3 parts and sketch the 3 parts. So let's do that. Here's the domain. And we want to sketch this function now. Okay, what are the 3 parts? Everything less than 0, 0 itself, and everything after 0. Those 3 parts. Okay, so on the left-hand side, that is everything less than 0. What do we sketch? For this first part, on this side, what do we sketch? X. Okay. So, what is that going to look like? It will be something like this. Open circle. Why do we put the open circle? Because it's less than 0, not equal. Okay. And we stop at 0 because the function is not defined after that. So f of x equals x only up to 0, not including 0. Okay, what happens at 0? The function is 2. So the function is 2. We just put a dot at 2. Remember back to what we said about graphs. Graphs is the set of points, x and y. That's the graph of a function. In this case, the graph of the function is just 1 point. So when you're drawing lines and parabolas, it's a whole lot of points. But here, the graph is just 1 point. So we do a big dot there to show it's 1 point. Okay, what happens after 0? One minus x squared. Yeah, what's that going to look like? It'll be something like that. Right, minus x squared, so it's a sad face, shifted up by 1. Not including. So we put a circle there. Everyone see what we did? Okay. So everything less than 0, that was f of x equals x, not including 0. Again, please keep this in mind. There, and there. Please keep those in mind there. Okay, so less than 0, not including 0. It is equal to 2 at 0, so we put the closed dot. And then after 0, it's 1 minus x squared. Again, open dots, we're not including that point. Okay, and notice how the function changes as well. So going from left to right, we've got f of x equals x. Then it changes to 2. Then it changes to 1 minus x squared. Okay, again, changes twice. So it was x, it jumps up to 2, then jumps down to 1 minus x squared. Everyone all right with that? Okay. Any questions on piecewise? Yeah.
So the point of piecewise function is to break down the whole graph.
Yeah, that's it.
To break it down to string lines.
Yeah, that's it. So if I want some domain, but on one piece I want one function, on another piece I want a different function, then it's piecewise. Why? We'll see that with the other functions. The functions you learned in high school are very baby functions. We've got the tutor there. You can ask him about the functions that you're going to be seeing coming up. Okay, parabolas and hyperbolas, you wish you're going to have that again. Okay, you can ask him afterwards about piecewise functions. Okay, but everyone gets the idea of what's going on. Yes? 1 minus x squared. So that's just this bit here. So it's minus x squared, so that's a sad face parabola, shifted up by 1. So we shifted up to 1 there, so this is 1. But that point along the y-axis, we don't include because of the x is greater than 0. Yeah, so it's everything that side. Yeah, so you've got this bit on the other side, the dotted line there, but we're only interested in positive, so we don't draw the dotted parts. So that goes away. Okay, everyone okay with that? Okay. Yes. No, just positive x, just x. Yeah, so it's just the straight line x. Yeah. Do you have a question? Yep. No, it can be anything. Yeah, so you can have a piecewise function with 2 parts to it. You can have 3, 5, any number. But for sketching, for the class test, only up to 3. Okay, so I won't expect you to break it up into 4 parts or anything like that. 3 parts, that should be fine. But again, for the tutorial, it might be more complicated. But test and exams, 3 parts, that'll be it. Yeah.
So it's a math information given to us, so we have to work it out.
This stuff. Oh, no, that's just the whole function that's given to you. Yeah, that's given. It's like if I give you f of x equals x squared, and I say sketch that.
So we're just sketching.
You'll see what's coming. You'll see what's coming. For now, it's just sketching. Yeah. Later on, it will get a bit more. Yeah. Injectivity. We can check. You can check that. So for this example, is it true that one input goes to one output? Yes. Yeah. If I give you -1, it goes to -1. 0 goes to 2. X equals 1, that goes to 0. One input, one output, it is injective. Is it surjective? No, it's not. Easy way to check, you cut the graph like this, count how many points. So here we've got a point over here, and we've got over there and over there. Do you agree that is the same y value? It's a horizontal line. They're all on the same y value, right? On the left, I've got an x value that gives me the y value. On the right, I have a different x value that gives me the y value. 2 to 1. So, surjective, not surjective? No. Good. Yeah, we can have surjective and injective with these as well. But always just think straight line and parabola. So a straight line, if you just imagine a straight line, it is injective because it's 1 to 1. It is surjective, right? Because it's one. Let's go back to the picture. This one here, this picture. So imagine a straight line. Any straight line, doesn't matter. It's 1 to 1. One input, one output. It is also surjective because range equals target. Okay, so straight line, injective, surjective, everything fine. Over here, problem. Okay, this is not surjective and injective. Is it injective? No, right? We did this over there. It's not injective. So just keep those two pictures in your mind. So if you want to think, is this injective or not? Think of that straight line example and think of the parabola example. So here we cut it with that horizontal line and we saw 2 to 1, not injective. Okay. And it doesn't go to all of the y values, so not surjective. Okay. So straight line, injective and surjective. Parabola, not injective, not surjective. So you can see between the two. So if we go back to this picture here, we see this is like that parabola picture. It cuts at 2 points, so not injective. And this won't be invertible either, okay, because it's not surjective, not injective. Okay. Everyone okay with that? Yes, no? Okay, again, just think of those two pictures. Straight line and the parabola. Okay, homework problem, and then we'll leave it at that for today. Okay, f of x is equal to minus x if x is less than 0, 1 if x is equal to 0, x squared if 0 less than x less than 1, 1 minus x squared if 1. Thanks. Okay, so here we've broken it up into 4 parts. So we've got everything less than 0, that's part 1. 0 itself, that's part 2. It's a single point, but it's still part 2. Between 0 and 1, that's part 3. Everything after 1, part 4. Okay, please sketch this for homework. Okay, so 4 parts, but remember the quizzes, tests, exams, and so on, sketching will only be 3 parts. Okay, so it doesn't take too much time. Right. Any questions on the homework? Okay, so for now, the piecewise functions, please make sure that you can sketch them. Okay, so for this week, if you can sketch them, that's fine. Next week, please start reading the next part of the chapter on limits. Okay, so reading for next week. Please do the reading. Okay, it's not just for fun. So reading for next week. Limits. Okay. So in the textbook, there's the sub chapter on limits. Please read that up to continuity. Okay. And then just a little note. So here. What's really nice about this learn page, let's go here to the textbooks, your textbook, student. I can see who's been looking at the textbook, which is quite nice. So let's show all. These at the bottom here have not opened the textbook, which is a little bit concerning because last week I gave a reading assignment. I said read on functions, right? Remember that? Remember when I said read the chapter on functions? How are these students reading the chapter on functions if they have not opened the textbook? Very interesting that you can read the chapter on functions, not even open it. Very interesting. Also, just while we're on that, let's have a look at the quiz solutions. Quiz solutions. Let's have a look at that. All of these here, from there all the way down, have not looked at the quiz solutions. All of these here, no, all the way down, have not looked at the quiz solutions. How do you learn from your mistakes if you don't look at the solutions? I don't know. Okay, so please keep in mind, I can see exactly what you're doing on the learn page. So at the end of the semester, when you come to me and say, sir, I got 45 for the class test, I do a little search for your name, and then I'll see, oh, you didn't look at the tutorials, you didn't look at the solutions, you didn't open the textbook. What did you expect? Okay. So yeah, please keep that in mind. I can see this person looked at it 7 times. It's pretty cool. But all of these no's, that's a problem, and that needs to be fixed before next week. Okay. Okay, so when I say read the next chapter for next week, go on to learn, get the textbook, and read it. Okay. Or when we finish the quiz, and I'll say the solutions are posted, go on to learn, open the solutions, and read them. Okay. Otherwise, we're going to have a big problem with the pass rates when we get to class test 1. And when people come to me and say, why is the pass rate so low? Well, no one's looking at the solutions. What do you expect? Okay. Please make sure that gets done.